capital R is a 3D region, right? So this isn't supposed to be flat, but I don't know how to draw it in 3D, right? So this is like a 3-dimensional blob in space. And we call the boundary of this region like the sort of the shell of the region, or like the skin of that blob. If we call the boundary the surface boundary of R, then this is true. By the way, F is a vector field. If you take the surface integral over the vector field, where the surface is the boundary of your blob, that's equal to the triple integral over the whole blob of the divergence of the vector field. So it's really hard to visualize this if you don't have a good imagination, and if you don't have like good computer animation software, right? But we watched a computer animation of divergence and curl not too long ago, and the idea of divergence is that a positive divergence means that point in your vector field acts like a source. Like vectors tend to move away from that point in your vector field if that point has a positive divergence. If the divergence is negative, that means that point in space kind of acts like a sink, like all the vectors are pointing towards that point in space if you have a negative divergence. And a divergence of 0 could mean that your vector field is 0 in that region, or maybe like all the vectors are just pointing one direction with the same magnitude. So some vectors are pointing towards that point, some vectors are pointing away from that point, and it balances out. So it doesn't really act like a source or a sink. When you talk about a vector field describing fluid flow, it wouldn't be a source of the fluid, and it wouldn't be a sink for the fluid either. So if you can imagine a region in 3D space, and the surface integral of your vector field on the boundary of the region, that's saying how much fluid is flowing out of the surface, if that surface integral is positive, or if the surface integral is negative, that's how much fluid is flowing into the surface. And what the divergence theorem is saying is that surface integral is equal to how much each point inside the region is behaving like a source or a sink, all added up and averaged in the way that a triple integral adds things up. So I know it's really difficult to imagine, and it's equally difficult to animate that sort of thing in 3 dimensions. But that's what it's saying. You really only have to know the formula. And we'll do a couple examples. This example says, verify the divergence theorem for the following vector field and the 3D region. So if your problem ever says to verify the divergence theorem, just start by writing the divergence theorem. And then what you're going to do to verify this is you verify that the left-hand side of the equation is really actually equal to the right-hand side of the equation. So what we would do for this problem is we would solve the surface integral on the boundary of the region over the vector field. And then we would also, on the right-hand side, we would take the divergence of the vector field and solve the triple integral over the whole region. So it doesn't really matter which one you do first, as long as we eventually do both of them. So I guess let's first look at this surface integral over the vector field. So for a surface integral over a vector field, the formula that I can remember is that this is equal to a double integral with some bounds of my vector field dot product with the cross product of the partial derivatives with respect to my parameters of my parametric surface, and then I take that integral with respect to my parameters u and v. And so my region is defined with these equations here. X squared plus y squared less than 4, what does that describe? It's a disk with radius 2 in the xy plane. And then z greater than 0 less than 3 would say let that disk live with any of the z coordinates between 0 and 3. So we're talking about a cylinder. This region is a cylinder in 3D space with radius 2 and height 3. Okay. In order to use this formula, I need to find a parametric surface for this boundary of the cylinder. But the boundary of the cylinder is actually going to be the sum of 3 distinct surfaces. There's the bottom of the cylinder, which is a disk. There's the top of the cylinder, which is a disk. And then there's the outside or the lateral surface of the cylinder. And so this is actually going to have to be the sum of 3 different surface integrals, okay? Because we have the bottom of the cylinder, we have the top of the cylinder, and then we've got the sides of the cylinder. Okay. Now for the bottom of the cylinder, if I write that as a parametric surface, I say x, y, and z is equal to some function of u and v. Of course, for the bottom of the cylinder, z is equal to 0. And I'm trying to map parameters u and v into coordinates x and y. I think sorry, I'm just trying to think about how, like, what's the best way to do this, or would be a nice way of doing this. What we might be able to do is try this and see if it works. If it doesn't work, we can try something else. But since this is a disk that we're going for, the bottom of the cylinder being a disk, what I'm thinking is we'll pretend like my parameter u is like the distance from the origin, right? And then my parameter v is going to be the angle from the x-axis. And so we're kind of like doing a polar coordinate conversion. I just renamed my parameters. Instead of my parameters being r and theta, we're calling them u and v, but otherwise this is the disk in polar coordinates. And in this case, I would say that u is greater than or equal to 0, but less than or equal to 2, because that's my radius. And then v is between 0 and 2 pi. Okay. The top of my cylinder is also needing a parametric equation. But in this case, it's going to be the same thing, but with z value of 3. And then, of course, the sides of the cylinder needs a parametric surface. And I think a good parametric surface giving me the sides of the cylinder is that x will be 2 cosine of u, y will be 2 sine of u, and then z will be v. And then we'll just say v can be anywhere between 0 and 3, but u has to be somewhere between 0 and 2 pi. And I think that does the trick. By the way, we also have to do something like this as well. V right there. Okay. So far, so good, maybe? Coming up with a way to parameterize the surface of a cylinder. So, this is probably a great time to talk about this, but if you're ever asked, what's the purpose of the divergence theorem, or like what's a good application, why would you ever want to use it? Why would you ever want to use the divergence theorem? It's because this is a pain in the butt surface integral to calculate, right? Like this isn't fun for me to do this surface integral over this vector field. And so the idea of the divergence theorem is saying if you wanted to calculate the surface integral over this vector field, you could instead do this triple integral. And we're going to do this later, but we're going to find out here in a minute that triple integral is really, really easy. It's just stupid easy to do this triple integral, but it's a huge pain in the butt to do the surface integral. So anyways, we're doing the hard part first, and the fact that there's a hard part and an easy part, that is the whole reason why the divergence theorem is useful. Okay, so let's start with this one, and I'll try to use green ink when we solve this surface integral. So this is going to be the integral from 0 to 2 pi of integral 0 to 2. And what goes inside here is going to be the scalar field f dotted with the partial with respect to u and partial with respect to v. And actually, I should probably just go ahead and find those partials and then take that cross product first before I try to set up the rest of this integral. So we know this is my r. This is what we call r here. So if I say, what's the partial of r with respect to u, that's going to be a 3 by 3 vector. And partial with respect to u here is going to be cosine v. The partial with respect to u here is sine v. And then the partial with respect to u here is 0. And then if I want the partial with respect to v, the derivative of cosine is negative sine. So negative u sine v. The derivative of sine is cosine, so I write u cosine v, and then 0. If I want that cross product, then this is going to be the determinant of this 3 by 3 matrix looking thing. And on the second row I have cosine v, sine v, 0. And on the last row I have negative u sine v, u cosine v, and 0. So this cross product is going to be a 3-dimensional vector. The first entry is going to be 0. The second entry is going to be 0. And the third entry is going to be u cosine squared v plus u sine squared v, which is just u times 1. Okay, so that is what goes in there for that cross product. 0, 0, u. Now, for the vector field capital F, that capital F is 2x negative 2y z squared. Did I copy that correctly? Did I remember it? I don't have good short-term memory. Let me check. Okay, cool. I have to replace these x's and y with the u's and v's, right? Or alternatively, I could replace the u's and v's with x's and y's, but let's just go ahead and convert x and y into u and v. So x is u cosine v, y is u sine v. And then z is 0 in this vector field. So this capital F is going to be 2 times x. So that's 2u cosine v. Then negative 2y for the next entry. So negative 2u sine v. And then for z, that's 0. Okay, take the dot product of these. And the dot product is 0. So if the integrand is 0, taking a double integral of 0 is just 0. And so that was all a waste of time. No, just kidding. But that part of it is 0, and I don't have to worry. I don't have to worry about any flux over the disk on the bottom of that cylinder, okay? There's no vectors passing up through the bottom or down through the bottom of the cylinder. And we actually could have kind of figured that out, okay, by looking at the vector field. Because if the bottom of the cylinder is flat, right? The bottom of the cylinder is flat. So there's not going to be any flux through the bottom of the cylinder unless there's a vertical component to the vector there. Okay, but the vertical component, or the z component of my vector field, has the formula z squared. But at the bottom of the cylinder, z is always 0. So there's no vertical component to the vectors at the bottom of the cylinder, so there's going to be no flux. And so it makes sense, just confirming that it makes sense that we got a 0 for that surface integral. Okay? So we just did the bottom of the cylinder, and we found out that that was 0. So we're going to add these together, and that's going to be a 0. Next, what we're going to do is we're going to take a look at the top of the cylinder and add that to our sum total surface integral. And I'm going to make some room here so we can do all that. Actually, a lot of this is going to be the same, isn't it? I maybe shouldn't have erased everything, but oh well. The partial derivative with respect to u of this is going to be cosine v, sine v, and then the derivative of 3 would just be 0. And then the same thing happens when we take the partial with respect to v, as it did before. So actually that cross product is the same. And do you remember what the cross product was? U. Yeah, 0, 0, u. Okay, so then when we set up my surface integral, we'll say du dv, and v had lower bound 0, upper bound 2 pi. U had lower bound 0, upper bound 2. Capital F is my vector field. And I know I'm about to do dot product between that vector field and 0, 0, u. And if you know how to do the dot product, you also know I don't care about these first two entries, right? Because I'm about to dot product and it's just going to multiply 0. Okay, so I really care about the last entry in F, and that entry I remembered was z squared, right? Well, z, at the top of my cylinder, z is what? 3. So that's going to be 3 squared. Okay? So my integrand is the dot product between stuff I don't care about and 3 squared, and then 0, 0, u. So my integrand here is going to be 9u. What?
Would it be negative then?
Why?
The dot product is negative and positive. Do you add them together or do you subtract them altogether?
In the dot product, you multiply the elements that correspond to each other, and then you add all of those products together. Yeah. Yeah. Okay. So if we take the antiderivative of with respect to u, this is going to be 9 halves u squared. And then if I plug in 0, it's 0. If I plug in 2, then that's 4. And then if I take the derivative, or the antiderivative of 1 dv, then that's just multiplying by 2 pi. So then the 2's would cancel. And then this is 9 times 4 times pi. Okay, so 36 pi is the surface integral of the top of the cylinder. The last thing we need to do for this problem is take a look at the sides of the cylinder, the lateral surface, and see if that adds anything to the sum of the surface integral of the boundary of this cylinder. Okay. I think that this is, it's not hugely different, but it's different enough that I'm probably going to just erase everything and start over from scratch. But I'll need to do the same process. So we'll take the partial derivatives with respect to u, and then the partial derivatives with respect to v, and then we'll think about the cross product, and then we'll think about what the capital F vector field formula looks like when I replace the x's and the y's and the z's with my parametric surface, and so on. But partial with respect to u is going to be a 3D vector, and that's going to be negative 2 cosine u. And then 2, oh, you're right. That should be a sine. Negative 2 sine u, and then 2 cosine u. And then the partial of v with respect to u is just 0. Okay. Then the partial with respect to v is going to be 0, 0, 1. Cross product of these is going to be the determinant of this 3 by 3 matrix looking thing, where I've got negative 2 sine u, 2 cosine u, 0, 0, 0, 1. And so this is a 3D vector. The first entry is 2 cosine u. The second entry is going to be negative 2 sine u. No, positive. Yeah, haha, I forgot minus j, right? I should just, no, I shouldn't, because that's just how the determinant works. So, yeah, and then the last entry's got to be 0 for that cross product. So I don't actually care what the last entry of f is. I know it's z squared, but that honestly doesn't matter because I'm about to do the dot product and then it's going to be multiplied times 0. So who cares that that is z squared? But the first entries are what? 2x and negative 2y? Let me verify again. Yeah, good. And 2 times x for us, looking at this sides, is going to be 4 cosine u. Negative 2y is going to be negative 4 sine u. And then z squared is going to be v squared. again, I keep saying I don't care about that because here in a second, whenever I'm writing my formula, I'm going to say du dv. So v goes from 0 to 3, u goes from 0 to 2 pi. I take dot product between capital F and the cross product over there. So capital F is 4 cosine u. Negative 4 sine u. And v squared. Oops. So capital F dot product times the cross product, which is 2 cosine u, 2 sine u, 0. All right, almost there. This is equal to integral 0 to 3, integral 0 to 2 pi, and then this is 8 cosine squared u plus negative 8 sine squared u plus 0. So I know there's a trig identity that does like, what is cosine squared minus sine squared? I just can't remember. Okay, so I remember cosine squared is the same thing as, I think, 1/2 1 plus cosine 2u, right? Is that right? Okay. And then sine squared is the one where it's 1/2 1 minus cosine 2u. And so if you do cosine squared minus sine squared, then that's 1/2 minus 1/2. And then it's half cosine 2u minus negative half cosine 2u. So that's just cosine 2u, I think, if you subtract them. So this is 8 cosine 2u, I think. I could be wrong, though. What did I say? 8 cosine 2u du dv. Okay. So now, taking the antiderivative of cosine gives me sine, and then I have to divide by 2 when I take that antiderivative. So 8 divided by 2 is 4. Integral from 0 to 3 of sine 2u, lower bound 0, upper bound 2 pi dv, which is 0. Yeah. So it turns out, I guess, the net flux through the lateral surface area of our cylinder is 0. That doesn't mean there's no flux through anywhere on the surface area, but it means the positive flux and the negative flux cancels out. And I think that's exactly what's happening because you remember the cylinder is radially symmetric about the z-axis, and the vertical component of all these vectors only depends on the height. So the vertical component is really only coming off through the top, but there's nothing happening through the sides because the sides themselves are vertical surfaces. So what I've got is like, positive stuff coming in the x direction for quadrants 1 and 4, and negative. Well, I also have positive flux in the x direction for all the quadrants. And then I've got negative stuff and y's, and the x and the y's are symmetric, but they're opposite. And so the positive flux through the lateral surface area is canceling out the negative flux. And that's how we ended up with the 0 there. So the total flux for this surface integral over the vector field is 36 pi. Okay? Is that good? All right. Now, that was brutal, and I hope we didn't make any mistakes, because what we're supposed to show is that this is going to give us the same thing, but it's a whole lot easier, I think. Okay. So, divergence of f. What's the divergence of this vector field?
What was it? Opposite triangle?
The little nabla operator that tells you, like, basically take the partial derivative of the first entry with respect to x, and the partial derivative of the second entry with respect to y, and the partial derivative of the third entry with respect to z, and then add up what you get. Add up those three terms. So the partial of 2x with respect to x is going to be 2. The partial of negative 2y with respect to y is going to be negative 2. And then the partial of z squared with respect to z is going to be 2z. And so the divergence of f is equal to 2z. Okay? So that means we're going to take the triple integral over the cylinder of 2z dv. Okay? Let me find some room to do that. The triple integral over the cylinder of, what did I say, 2z dv. And so I'm going to go ahead and parameterize the cylinder with cylindrical coordinates. Believe it or not, cylindrical coordinates work really well for cylinders. So let's do that. And in cylindrical coordinates, I'm going to say theta goes from 0 to 2 pi. I'm going to say that my radius r, the radius of the cylinder was 2. So r is going to go from 0 to 2. And then I've also got dz, and z went from 0 to 3. I also get a little r. Remember r d theta? That comes with the order of integration. That comes with converting to polar coordinates, converting to cylindrical coordinates. Okay, and then the meat of this is 2 times z, so I'll put the 2 outside, and then the z in cylindrical coordinates is still z. So we're good to go. Antiderivative with respect to z is going to give me z squared over 2. So I'll just forget about that 2, and this becomes a z squared. The z squared, I'm going to plug in 0, and that makes it 0. And I'm also going to plug in 3 for the upper bound. So 3 squared is 9. And 9's a constant. So this is going to be 9 times definite integral from 0 to 2 pi of definite integral 0 to 2 r d theta. Okay? So antiderivative of r, oops, jumped way too far down, is going to be r squared over 2. So right, 9 over 2. Okay, but then the r squared part is going to be 2 squared minus 0 squared, so that's going to be 4. And so that's 4 and 2 and 9 make 18. And then the integral from 0 to 2 pi d theta is 2 pi, which is 36 pi.
That is so much easier.
Yeah, exactly. So that's the point of the divergence theorem. We verified that it works, at least for this example. But the point is that oh man, that was tough to do 3 different surface integrals to get the bottom disk of the cylinder and the top disk of the cylinder and the surface around that lateral surface area of the cylinder. And, I mean, I think, honestly, this is the hardest part of the problem, is just figuring out how to parameterize the different surfaces that make up the boundary of a region. That's hard to think about. They're hard to solve. It's a pain in the butt to do, like, cross products and dot products and all this crap that we had to do. So if you are asked, if you take an exam and somebody asks you, solve, the surface integral of a vector field over the boundary of some region in space, think to yourself, oh yeah, well, the divergence theorem tells me I could just take this triple integral and take the divergence of that vector field. And that's usually a heck of a lot easier, a lot fewer steps. Okay. We probably don't have time to finish this example, but Abdullah had asked me if there was a way to calculate volumes of three-dimensional objects using surface integrals over vector fields, and the answer is yes. And this was going to be an example. And this is a problem that I guess I could ask. I could ask, what's the volume of the three-dimensional region that's bounded by the following parametric surface? And so you might recognize this. This is a parametric surface for a torus, like a donut shape. What you might try to do if you wanted to find the volume of the torus is you could say, okay, let me think about, what do you call it? The divergence theorem. You could think about the divergence theorem and think, if I take the I'm going to call this torus R. If I take the surface integral over the whole boundary of this torus, and I know what the surface is as a parametric surface already. I've already got that. Of some vector field f, this would be equal to the triple integral over the region itself, like the interior of the torus, of the divergence of f. And so we learned in a previous lesson that if you were to take the triple integral over some 3D region of 1, this is the volume of that region, okay? So the question that we could ask ourselves is, what vector field f has a divergence equal to 1? Because if I could make the divergence of the vector field equal to 1, then I could make this triple integral be the same as a surface integral over the boundary of whatever that vector field is. And I think there's a lot of vector fields that have divergence equal to 1. For example, one vector field that has divergence equal to 1 would be x over 3, y over 3, z over 3. Because whenever I take the divergence of f, this is the partial with respect to x of x over 3, plus the partial with respect to y of y over 3, plus the partial with respect to z of z over 3. So it's 1/3 plus a third plus a third, and that would be equal to 1. Does that make sense? So what you could do, I'll leave it to you to try it in your own time if you want, is you could say, let me take this surface integral using this surface, this parametric surface over here, and the vector field, let it be this vector field right here, and then that should give you the volume of the torus. Of course, there's easier ways of finding the volume of a torus, right?